Hello, Kennedy. Hello, Spencer. Let's see who is here. Hello, Connor. Hello, August. Nice seeing you connected. And many thanks for waiting. So, the most important remaining part of the class are research projects. The most complicated part of the remaining part is to start. Then, after everyone starts, it will roll over naturally. And we will start 1 week later because of the special schedule. So, and I don't know if coming this week, Wednesday, we'll do it during the 5 p.m. 5 p.m. Please try to log in or come in person. The plan is that I will make maybe 10 minutes long one-to-one personal interviews and suggestions how to adjust code according to your selections. So even if you are not coming in person, of course I'm open to do it anytime, but during the class it will be more organized and it's a dedicated time for this activity. What are we going to do today? So again, thanks for waiting. I reviewed the length of the material for today's lecture. We will not finish it in time. There will be leftovers for next meeting. But the plan is multifold. So I will have a glance again on your choices and remind you what it is. Then I'll show a protocol, a manual for completing your individual research project. Right now it is a little premature, a little too early because before you set up your potentials, but it will give you heads up what to expect. So it will be basically suggestions after you design potential, how to run, what to store, how to analyze, and how to safely arrive to written report and presentation. So it's basically an algorithm of mini research. Then I'll probably show a mini research that I'm doing myself, that those who didn't select subjects may decide to take. And then we'll go to the didactic academic class material. So let me announce what we are going to do, and then I'll just automatically go through the slides with increasing speed. So we are in the physical chemistry course. The overarching goal is to understand, interpret, predict outcomes of the characterizations, of the measurement of molecules, materials, their properties, their ability to react through understanding the internal laws of how they behave. We already agreed that it is one of the key features is wavy nature of electron, and we are not giving it up. We will return to it very soon. At the same time, we admit, or I admit, and you were not protesting, that light, small nuclei like protons also exhibit quantum properties, and there are certain circumstances when one needs to take into account. Right now, we are having the tactical, local goal to see what would happen to interatomic bond that is able to oscillate harmonically if it is excited, irradiated by infrared laser in resonance with its frequency, with admittance of the fact that it is not a classical oscillator, but it is a quantized particle. In order to achieve this goal, we are studying the concept of so-called coherent states, or it was introduced as eigenstates of the annihilation period. Last time, for about 2 meetings, we did found eigenstates of the annihilation operator in the discrete basis. And I will quickly review our achievements from last lecture. Today, and probably there will be leftovers for the Wednesday, I will do the same in the basis of continuous distribution, which is a little more natural for humans, and then combine them together. And all these efforts are preliminary steps to see what happens to a molecule when it is irradiated and starts. Intuitively, we expect that it will just oscillate with larger amplitude, but we know that position is not a good feature for quantized particles. There is a distribution. Okay, I'm going to these slides and let me see. There's one message. Good morning, Spencer. Okay. So focusing here, starting to share, and going forward with the slides. So here are your choices. I still do not have a written record of 3 choices. So August, you may you do not if you you may either modify online file, or you can write me privately in the email. Adam, I'm not sure if he's planning to complete the course, but if you're Adam, if you're watching, it is a key part of completing the course. Even those of us who get excellent grades through the course will not automatically extrapolate it without doing the project. And Tim, I think he's watching. Tim, please select your project. So just little stuff that mini project that I'm doing and no one selected. So it is based on very recent publication. It is like what scientists are excited about. So sulfur, the most common form is cyclic with 8 atoms. And if it is pressurized with methane and hydrogen, it converts into hydrogen sulfide, and under like 1,000 times bigger pressure, it becomes superconductor, which like is exciting. Superconductor at room temperature. So here is the molecule with frontier orbitals, and the gap is quite big. If one starts to irradiate it by light, then the gap becomes smaller and smaller, and then arrives to a 0 value. 0 value is not sufficient, but it is mandatory criterion of being superconductor, of being metal. And there are some other evidences like growing pressure and temperature, which is expected to cool down after reaction is done. Here, maybe it will work, maybe not. It's just some movies how this ring is broken, and few H2S molecules are formed. And then it will be like continuous distribution of H2S, methane, and hydrogen that eventually arrives to superconducting phase. So here is the stuff that I did announce, the protocol for your research projects. Basically, if you literally go through each step, it is a guarantee of successful completion of the course. And even if you are missing some previous like homeworks, it will cover everything. So I will not read line by line, but first thing is not included here is to select a potential and program it or import it from external data. Then set up a wave packet and see how it moves through. So if your problem is electronic, it will correspond to electron moving along the molecule or through interface in materials or along the polymer. No, you didn't select, or you selected the charge transfer.
Yeah, Marcus theory.
Okay, Marcus theory. Some of you have likely selected chemical reactions when stuff is coming over the barrier. And one may want to try to run the dynamics with values of momentum corresponding to different temperature, different kinetic energy, substantially lower than expected activation, substantially bigger and equal. And look how the dynamics is changing if you are exploring these regimes. It is expected that above it should go over, below it should reflect and not go anywhere. But there are several ways to quantitatively characterize this overcoming of the barrier. And for the sake of the time, I'll go to the next point in the agenda, but I will distribute this stuff and maybe focus on it again and again for a couple of times. Okay. So 2-3 meetings ago, we were looking for eigenstates of annihilation operator in discrete basis. We did found that expansion coefficients of this unknown eigenstate obey recursion relation. Recursion means return to itself again and again. And this connection of lower order to higher order allows to find everything if you do know the very lowest one, C naught. In order to find C naught, we used the normalization condition. And when we were practicing it, we found that normalization condition demands C naught absolute value squared times the sequence of the leftovers from this summation of all coefficients of the higher order coming into exponential, and exponential of this mu square e to the power absolute value mu squared. This can be solved for C naught. To be rigorous and precise, one needs to have the absolute value here. And we are coming to a situation when there is only one independent parameter that we still do not know, eigenvalue of the annihilation operator. As soon as we know this mu parameter, we can find C naught and we can find C sub n for any rank. So we did stop at this slide last time, and I believe I was mumbling it with the accelerated speed so that no one recognized and memorized, or maybe you did, then you are above expectation. But I'll go over once again. Before diving into equations, let me quickly check if there are any questions and suggestions online. Kennedy, Spencer, Connor, and August. If you want to ask any questions or request any comments or change the program of the meeting, please let me know. I'll count to 3 and then continue. Questions? No questions. Questions 1, questions 2, questions 3. Okay, I'm going back to sharing. So, first, first line here is the eigenstate of annihilation operator, where we know everything except the eigenvalue E. So we have the factor here that comes due to normalization. Then we have ramping power. So we have eigenstates starting from 0. Those are eigenstates of harmonic oscillator. And coefficient in front of each coefficient number n is eigenstate to the power n and square root of number. how do numerator and denominator behave as function of n? Like if mu equals 2, like 2 to the power x or 2 to the power n, is it does it grow or decline? If you have number bigger than 1, and we have power going 1, 2, 3, 4, 5, will the result increase or decrease?
Increase.
Drastically. If we have a square root of n, how does it behave with n? Increase or decrease?
Increase.
Increase. And if you have 1 over square root of n, it will decrease. So we have two monsters. Both are raising. Like it's King Kong versus Godzilla. And we numerator and denominator. So we need to look which one will win. Right? And later we will see that the monster in the denominator is stronger. So as soon as n goes to really big numbers, it will win all the time. But at the early stages, numerator may win. And if mu is smaller than 1, then denominator will win automatically. Right? So next thing, through the way of predicting future by eigenstates expansion, we may recall that the wave function of the future can be obtained from the wave function of the past by multiplying each eigenstate in this expansion by e to the power minus I over h bar e sub n times time. Right? So here I suggest that we submerge this dependence inside this cat notation, and what we call n of t, it's not the number is changing over time. It's a quantum state number n is changing over time. So, and there is one line missed here. N at time 0, or just simply n, times e minus I h bar e sub n t. So our definition of quantum state number n as function of time is quantum state n without time dependence with this time dependence. Okay. We do know that energy sub n. By the way, if you are planning to take next class in the PChem series, PChem2, and you are wondering, do I need to remember any equations, or can I wipe off my memory as a main principle of undergraduate studies? Pass exam, forget everything. At least it was my principle at the time. So there is at least one equation that I guarantee will be used in the next PChem class. And this equation is this one, E sub n. So can you please help me to remind it? Energy of the state of harmonic oscillator number n. And it is on this slide. If you're careful with it, you will see it anyway. So try to scroll through your memory or just analyze this slide. I'll make a little pause for this notation. Insert display. So here is the little non-logical picture when one shows potential and quantum energy along E sub n y-axis. Here we have x, and here we have E naught, E1, E2, E3. First question, E naught, is it 0 or below 0 or above 0?
H bar W1/2.
Thank you. Then H bar omega times 1. So what about E1?
H bar W3/2.
What about second?
H bar W5/2. H bar W3+1/2.
So overall, number n comes here, right? So the offset of all states is the same. And it is very cool. It is the reason why this model will be used in the next class, because it's mathematically very easy. In all other quantum states, as you saw in the particle in the box, the offset grows. In other systems, it declines. And here it is the same, which is quite cool for any mathematical processing on one hand. On another, oscillators are quite frequent because all molecules oscillate. So this equation is used here. I'm plugging in E sub n as h bar omega times n plus 1/2. So h bar is it is in the power of the exponential, and the E sub n contains h bar plainly in the numerator. This exponential has h bar in the denominator, so h bar cancels. After h bar cancels, we do have imaginary unit and time as a heritage from quantum definitions, and the rest here is a heritage of the energy. You see? So number n plus 1/2. So 1/2 is constant. I apologize for saying trivial things. And if we exponential to the power of summation is a product of exponentials. So this everything 1/2 and its factors can be put away from the exponential as a product, because it will be the same independent of what n is. And then the rest is minus I n omega time, minus I n omega time. And then the time independent eigenstate of the harmonic oscillator. So it is how the eigenstate of harmonic oscillator evolves over time. And if we need to find specific solution, it will be superposition of such stuff. So this exponential, this imaginary power means accumulation of phase. And if you draw real or imaginary part of the thing, it will be the camel with as many humps as a big number n is, and these humps will go up and down dynamically, right? Which brings, and they will go up and down as quicker as big the number n is. So the lowest order will change slower, higher order will change quicker. Okay. And then, you're not bored? Yeah? Okay, thank you. Let me know if you're bored, then I will switch to jokes and stories. So that we do not lose audience. So, going to the next line. This part can be placed away from summation sign. And then inside the summation, we do have an interesting observation. We do have the eigenstate, time-independent eigenstate. And we do have expansion coefficient. Now, this expansion coefficient is time-dependent. And I know that I stole part of it and put it here. But mathematically, if you look here, you may try to race with me and bring an observation earlier than I declared. Do you see any symmetry, any way to simplify an equation? And there is no big intrigue. It is shown in the next line. But what is the logic? So let's look here.
The n in the power is the same on the exponential and
Exactly. The power of mu and power of exponential is the same. So we can, thank you. So we can look at this box as mu to the power n times e minus I omega t to the power n, right? And then, since there are two numbers in the same power, we can convert it into mu times e minus I omega t to the power n. You allow me to do so. There are no protests. Okay. If we do so, there is a next step, which will be very appetizing mathematically. We have n number in the power n, square root of n factorial, and then eigenstate. So we basically come to the same shape as it was before, but instead of time-independent mu, we have time-dependent mu. So in some sense, we can say that we can make several observations. So by all efforts we did here in class in previous lectures, we can say that the construction in the first line is an eigenstate of annihilation operator if mu is eigenvalue. Let's look here. This line does satisfy requirement of eigenstate of the annihilation operator under the condition that mu times e minus I omega t is an eigenvalue. I don't know how to say it better, but I would really appreciate if you try to verbalize the same idea with your own thoughts. So please try to write it down. And then I'll ask you to verbalize. Just try to write it verbally. in case you didn't start yet, I'll repeat the question. So if we know that top line is definition of eigenstate of annihiilation operator, what can we say about the lowest line? Based on their similarities and differences. Basically, would it be possible to tell that the lowest line is also an eigenstate of annihilation operator? And what would be the eigenvalue for such an eigenstate? Let me check if any of the online attendees want to verbalize or type how to interpret the last line in the last slide. I do not see volunteers. I do not have a way to mandate it if there is no enthusiasm, but here it is a little easier. So, Jared?
I said the bottom line would also be the definition of the annihilation operator if mu of n.
Eigenstate. Eigenstate. Okay, continue.
If mu of n equals the mu exponential negative by omega time to the n.
Perfect. Do you have any, your own way to? We just.
So I said that since everything's the same, top and bottom, except the e to the minus I wt over 2, that was a state.
Okay. And we do have factor over 2 here. So maybe one can also try to combine these two stuff so that it will be the mu will include this time dependence. So there is a way to, we can practice it later, but I agree with the proposition of the chart. So that this is very, very similar, basically identical to definition, to proved, derived definition of eigenstate of annihiilation operator, but it will be correct only if the eigenstate, eigenvalue will be time dependent. So if the eigenvalue is not static, but if it will depend over time this way, then this will be eigenvalue. This is kind of crazy. All experience of us in the class and all experience of scientists practicing quantum theory until about 1960 was telling that typically eigenvalues of any operator are just static numbers. And here we see that eigenvalue must be dynamic. It's a little non-usual, but it's very healthy for the applications. So now I'm arriving to last slide of previous logical lecture where I wanted to arrive. So if we admit that eigenvalue depends over time according to this law, then this time-dependent eigenvalue plugged in here will give time-dependent eigenstate of initiation operator. So by browsing in this foggy, dark forest, we start to sense and touch the property of the object. So the eigenstate and eigenvalue of annihilation operator do not commute with Hamiltonian, and they do not need to be static. They synchronously change over time. But still, at each point of time, it is expected to be eigenvalue and eigenstate of the annihilation operator. So I'm very behind my own schedule, but before I go to the next segment of equations, which we will continue on Wednesday, I'll briefly tell. You probably are tired with abstract math and need more applications for physical chemistry. So there are several ways to remove interatomic bond from the equilibrium. One way is to excite it with infrared light, which means periodically change electric field, which means add slope to the potential, which means the potential will go left and right periodically, and then it ramp up and increase amplitude of oscillations. Another, same as another way, and those of you who selected Marcus may focus carefully on maybe next 30 seconds. So in ground state and in the excited state, or different electron state, potential energy surfaces, how the potential energy for bond changes with different changes with distance, can be quite different. If one excites the model from ground to excited state, the potential is changing. It may stop being harmonic, or it may stay, keep the harmonic nature, but it may change curvature, and specifically it may change the equilibrium position. So if one has ground and excited state, and if one uses optical or UV pump, then the eigenstate of the nuclear motion that was in ground state for the ground electronic state will be something that is not an eigenstate in the upper potential. But, and it is my task for our next meetings to prove that it will be eigenstate of annihilation. And it will be like distributed wave packet that will start moving forwards and backwards. So it will be something that characterized with this time-dependent eigenvalue and the eigenvalue of annihilation operator. And the shape of the wave packet will be mathematically belonging to the same class of equations, same equation, but it will move forwards and backwards in space. So I'm not defining it right away. We are slowly approaching to this declaration by small steps, but when we arrive there, I will go over and make sure that the building, the pyramid is in place. So at least we have a minute to start today's lecture. And the expected outcome of today's lecture is to see that eigenstate of annihilation operator in continuous distribution, not in discrete states, but in as function of position, will look very similar to the ground state of harmonic oscillator. Basically, it will be Gaussian wave function, right? You recognize exponential minus distance squared. sombrero, Mexican hat. Okay. But center of this normal distribution will be traveling. Will be traveling forth and back as a cosine function with a frequency corresponding to frequency of the oscillator. So it will be going forwards and backwards, and this shape, this Gaussian bell, will go forwards and backwards periodically. This is quite a trivial thing that one can immediately get in MATLAB, but to get it with pen and paper mathematical derivations, it's you see it takes a little longer. So there is no time to continue. Looking forward to see you on Wednesday on morning for the lecture and evening for the project. Meeting is dismissed.